The deep ocean is a uniquely hostile environment. Drop below 1,000 meters and you enter a world of absolute darkness, freezing temperatures, and water pressure strong enough to crush a steel hull. Yet some of the ocean's most successful surface hunters deliberately leave the sunlit waters and dive straight into it. Surviving that descent requires intense biological engineering. Marine predators have evolved thick insulating blubber, specialized heat-exchanging blood vessels, and lungs that actively collapse to prevent nitrogen buildup as the pressure multiplies. They pack their muscle tissue with oxygen-storing proteins, allowing them to hold their breath for hours, and their eyes adapt to capture the tiniest fragments of light, letting them operate where most other life forms would quickly perish. Which raises an obvious question: if the surface is rich in food and warmth, why burn massive amounts of energy to plunge into a freezing abyss? For a long time, marine biologists assumed the extreme deep was a barren wasteland to be avoided. But these dives prove it is a specific, sought-after destination, sparking a scientific race to follow these animals into the dark and observe what they actually do down there. Human divers obviously can't survive these depths alongside a migrating predator. To understand the dive, researchers have to attach electronic tracking tags to the animals while they are still at the surface. Researchers adhere these sensor packs directly to the animal's skin or fur. Once attached, the devices continuously record depth, ambient temperature, and bioacoustic audio. These tags eventually fall off and float to the surface to be retrieved. Until they do, they are the only link we have to an entirely hidden ecosystem. Where light fails and traditional cameras go blind, these temporary data points become our eyes, finally showing us what waits in the extreme depths. The first major pattern revealed by the data is that these predators are commuting to work. The midwater region, known as the Twilight Zone, is actually a dense, calorie-rich feeding ground. Between 200 and 1,000 meters down, the ocean is packed with life. It is filled with complex gelatinous organisms and large muscular squid that use the dim light as a refuge. Sensor logs show apex predators frequently targeting these exact depths to hunt. The data points directly to dense populations of spiny-toothed bristlemouths and lanternfish, which illuminate the dark with their bioluminescence. We can see this hunting strategy perfectly in the Chilean devil's fish. Tracking data shows this giant ray diving deep and simply hovering at a single specific depth for hours, waiting patiently to ambush localized prey. Sharks exhibit a similar strategy, using natural ocean geography to their advantage. They seek out massive deep-water gyres, columns of relatively warm water trapped within the cold abyss, because these pockets act as natural traps where prey species assemble in high volume. The sheer density of food in these deep pockets creates a highly concentrated buffet. For a predator, the massive calorie burn required to survive the freezing descent is mathematically justified by the feast waiting at the bottom. But hunting is only one reason for the dive. Sometimes the extreme depth serves an entirely different purpose. It acts as an emergency panic room. Take the common tuna. They spend plenty of time migrating and feeding near the surface, highly visible and exposed to anything larger than they are. Over a decade ago, marine biologists at Oregon State University attached small speakers to seals and played the sounds of killer whales. Invariably, the seal's immediate reaction was to drop everything and dive violently into the abyss. This chart maps a tagged tuma's evasion dive. The depth line plummets rapidly past 300 meters, indicating a desperate escape. Suddenly, at 326 meters, the light meter registers total blackout and internal temperature spikes. The tuna was swallowed whole. Even with occasional failures, this evasion strategy is common across marine species. The crushing weight and absolute darkness turn the hostile depths into a reliable survival tool against larger threats. If we push even further down, past 1,000 meters, the ocean reveals a third utility. For many species, the deep functions as a global infrastructural network. Researchers fitted pilot whales with specialized acoustic emitters. These are deep-diving dolphins that rely heavily on echolocation, and the sensors recorded their clicks accelerating as they tracked prey in absolute darkness. The physical properties of the extreme deep make this highly efficient. Under intense pressure, sound waves travel much farther and with greater clarity than they do at the surface. transforming the abyss into a long-distance communications highway. Magnetic signals from the Earth's core are thought to be significantly stronger and easier to detect at these extreme depths. Bluefin tuna likely dive here to lock on to these intensified signals, using the deep ocean as a high-precision biological GPS to guide their migrations. Beneath the turbulent waves and chaotic weather of the surface, the deep ocean provides a stable, hidden transit system that enables global marine migration. By tracking the movements of these apex predators, we can stop viewing the ocean as a flat expanse of water. It is a fully active, three-dimensional biological arena where the extreme depths are entirely integrated into the daily routines of surface life. Yet, for all we've learned from these sensor logs, the deep sea remains a largely unobserved territory. Most of the ocean's interior remains hidden, its biological interactions still invisible to human eyes. The next generation of technology is already aiming to close that gap. Engineers are developing miniaturized depth sensors and smart cameras capable of capturing and transmitting high-resolution imagery using only the faintest ambient light. By piggybacking on the natural diving habits of the animals that already know the way, human technology is finally on the verge of illuminating the darkest and most hostile regions of our planet.